Well, it is a pleasure to be here, ladies and gentlemen. I do like these meetings. They have lots of very interesting speakers and lots of very interesting topics. What I'm going to talk to you about today is the idea that aspirin can protect you not only from heart disease, but also from cancer. And last year, we developed a model taking blood out of people and patients from Bradford Royal Infirmary, and found that we could detect which people were susceptible to cancer and which people might be on the way to getting cancer. And I might say at this point that the British government have given us £1.2 million to try and take this to market. Not me, but some entrepreneurs who are going to do it. But based on that system, I thought it might be useful to use it for looking at aspirin and ibuprofen. There's a man called Sir John Burns in Britain who believes that if people take the right dose of aspirin, they can protect themselves for a long time. So I wanted to look at this and see what we could do with it in the system that we have. Just see where... Sorry, this... the top one. Okay, thank you. Right, now we're looking at these non-steroidal anti-inflammatory drugs, these NSAIDs, and these inhibit the COX enzyme activity that has been discussed with our speaker, and this is a mechanism of action of NSAIDs. Inflammation is associated with increasing cancer incidence, and recent preclinical and clinical studies have shown that NSAID treatments cause anti-tumor effects in cancer. However, they're very lengthy and expensive, and Sir John Byrne, the man that I was telling you about, is seeking £5 million to do an epidemiology study to prove that this might be useful. So how can we do studies like this? First of all, as most of you know, when you work in with humans, you have to get no end of ethical permission approval. And the other thing that we're interested in is nanomaterials. Nanomedicine is big hot news at the moment. And we wanted to combine this with this method that we have. So as we go down, we've got the various ethical permissions from Leeds. And how do we measure the nanomaterial that we're using? You can't just use it. You've got to check its size and so on. And it was measured by dynamic light scattering and zeta potential. And my background is genetic and reproductive toxicology. So genotoxicity, I don't know how many of you know much about it, but it was measured in this very simple assay called the COMET assay and micronucleus assay in lymphocytes. And this actually, micronucleus measures chromosome damage. And aspirin and ibuprofen were used to treat the lymphocytes in the bulk and nano forms. So ASP-N is aspirin nano, ASP-B is aspirin bulk, IBU-N, the nano form, and IBU-B, the bulk form. Treatments are a bit arbitrary in these assays, but we use 30 minutes in the COMET assay and 44 hours incubation in the micronucleus assay. But you have to work with the times that give you the responses. And we tried another technique called the patch clamp physiology, which was to see how the ion channels were affected in the cells. Now, this is the particle size and the volume mean diameter of the bulk powder, and the bulk powder is, you get it as you receive it. And you can see that the particle size here in micromolar for the ibuprofen was 52.80, and the volume mean diameter is 20.50. And this is quite high because it's bulk, and aspirin is 78 and 44. A minute. And the, let me just if I missed one. Sorry. Anyway, the nanoparticle size is 1,000 below that. And here we've got a picture. We did have a picture. Just to show you. 1 second. Well, I must have missed the slide, but it's 1,000-fold less for the nanoforms. This is the population we looked at. You have to try and match age if you can, as well as you can. We've got Caucasians and Asians in the population. In Bradford, we have many members of the Pakistani community, so they constitute our Asian population. So they're included, and obviously we have 3 different types of disease states that we're looking at: asthma, chronic obstructive pulmonary disease, and lung cancer patients. So we then have to compare them against the healthy individuals. And 40 in the COMET study, and 13 in the micronuclear study. Now that doesn't sound like much, but that's quite an enormous 13 micronuclei assays. And we also had lower numbers in the ion channel one. Right, here you can see the DNA damage. In this COMET assay, you use 2 measurements. One is the olive tail moment, so called after a lady called Peggy Olive, and the percentage tail DNA. And here we've got in different colors the untreated, we've got the healthy controls, the asthma population, the COPD, and the lung cancer people. And here we've got the untreated lymphocytes, aspirin bulk, aspirin nano, ibuprofen bulk, and ibuprofen nano. And lung cancer is obviously higher because it gives more damage. But I think if you just eyeball those data, you can see here that this one is generally lower than the aspirin bulk and down within the control range. And if you look at the ibuprofen bulk, the nano version is also lower. These are statistically significantly lower than these, the bulk versions. And this is a pattern that we're now going to see throughout, that the nano form is actually better for these cells. Don't forget, these cells come straight out of the body. They've got all their metabolic processes intact. This is the tail DNA version. And if you just look at some of these figures here, that is 10.9, and the aspirin nano version is 8.9. That's significantly different from that. And the bulk, 10.9 and 9.3. That's different from that. And asthma here is 17.4, and the bulk, the nano version, is different from that. And here, these are some figures to show you that there is these sort of differences. Now, here on the whole, we have got this drop with the nano version. Does that say that instead of taking aspirin as it is, we ought to be looking at the nano version of it? I'm not saying that yet. It might be a good idea if we tried in patients, but this is what it's showing in this sort of in vitro study. Sometimes you do get increases, but they're showing something different. So I'm not going to concentrate on that at the moment. I'm just concentrating on this reduction with the nano. There are other reasons for some increases, because the lung cancer can exacerbate responses, and asthma can be quite exacerbated by the presence of aspirin. Now, there's the picture here showing you what I've just shown you. And again, we've got different values of the tail DNA. But here, I think you can see that this is the bulk version versus the nano version, the bulk version versus the nano. And so you can see the differences in the different groups there. Confounding factors. This should be a 0 there, but you can see we checked confounding factors like age, smoking, ethnicity, drinking habits, and gender. And in fact, there were no significant differences. So that was for all the patients that we looked at in the group. They have to be checked for. I'm not expecting you to read all out. This is just called a micronucleus assay, in which you have to use so many parameters. But the parameter that we're interested in, this is a binucleate assay. And this, you probably can't see that from where you are, but I'm going to tell you that here's a value, which is 19.96, and that's the bulk version, and the nano version goes down to 5.6. The ibuprofen bulk here, this is 25.33, and it goes down to 8.6. So this sort of response is coming up in yet another genetic assay, so that you get a good reduction with the nano version. And if we go down this line like this, here we've got the asthma goes from 29 down to 10, and the ibuprofen goes from 44 down to 27. If we look at the lung cancer people, it goes from 20 to 28.3 down to 18. And coming down those columns there, there's quite a marked reduction with the nanoforms. That's really all you need to know from this actual slide, that in two different systems, we get different responses with the bulk and nano versions. Now, this is where we were looking at the ion channel changes. These two just tell you that we've got the ion channel systems working, but this is what the actual result is. We had ibuprofen only in this experiment, the ibuprofen nano version and the bulk version, and one is coming down here, and the difference in response, this is about 20% difference. And what it is known is that this actual nano version here alters the ion channels, which can actually give you a difference in response. I think you can probably see that from the back, that there is a difference here. So, where have we got to with this sort of study? This is the nearest you can get to taking man and using a tissue from man, which is blood. So what we found in here is when comparing the bulk and nanoparticle versions of aspirin and ibuprofen, both assays, DNA damage was decreased in lymphocytes from healthy individuals. Asthma, COPD, and lung cancer patients after treatment with the bulk and nanoforms when they were compared to the bulk version. Now, you could compare them to the untreated lymphocytes as well, which is what some of the other statistical values were in there. But in all groups in the COMET assay, aspirin nano caused DNA damage, which was significantly decreased in all groups except the asthma group. Now, on the whole, the asthma people tend not to get cancer. In the COMET assay, ibuprofen nano caused DNA damage, which decreased in healthy individuals and the lung cancer groups, but increased in the asthma and COPD groups. And in the micronucleus assay, micronuclei increased after aspirin and ibuprofen in the healthy individuals and lung cancer groups, and decreased in the COPD and asthma groups, except for ibuprofen nano in the asthma group. So what do all these data tell us? Well, based on what we did with our sensitivity assay last year in the lung cancer patients and disease patients en route, we think that this gives a fairly good indication that nano can be quite useful, maybe usefully used, instead of the bulk form. And some of you might say, why are you thinking of nano when aspirin itself can dissolve in water? If you take it, you often take it with a glass of water or whatever. This is because there's a differential in some of these aspirin and ibuprofen that you can buy. And this was set up because it was useful to set up in this way to use as a model to see what we could do if we made this bulk and nano form. And this has shown us something that maybe you can use these assays as a marker. I'm not going to say as a biomarker, but as a marker to actually give you some indication of what happens or could happen in a population. The studies that I was talking about, the sort that Sir John Burns is going to do with the asthma people, don't forget the cancer people. It can give you, aspirin can upset some people quite markedly if they take it, and some people are advised not to take it. But if you could have a different form that didn't irritate the stomach or whatever, this might be useful. So this was a model to see if what we could do with it, and I think it does hold promise because those other studies, the epidemiology studies, are very, very expensive. These are much cheaper and might give you some indication of what to do in future. Okay, so thank you very much. That's all I want to say today. Thank you. Sorry, I missed one slide on the end that just says that the patch clamp could be useful because it can detect early membrane damage as well. Thank you for listening.
Okay, thank you. Questions?
Here we go.
Thank you for a very interesting talk. I'm just wondering, then, is it a proprietary, or can you explain to us what's the carrier of the nanoparticles, and did you analyze the carrier alone?
Yes.
The effective carrier alone.
Materials, yes.
Yeah, and the nanoparticles, what
yes.
was...
I haven't got all that in here, but the man who made these particles for us put them in a carrier which was inert, and was there's a lot more information than I can put in here, but he's done a lot of work on the differences.
And you know what was the and what was the inert material?
The inert material?
Yes.
No, I'm sorry, I might have it in my, I'll have to look at it, but it was inert. He said it was okay. That's all I can tell you.
Okay, thank you.
Thank you. Diana, I wasn't quite clear. So when you're treating the cells with the nano versus the bulk, yes. Is the dose that the cells are getting in terms of material the same?
Yes. No. It gives you the same survival. So before we could do these studies, we had to do dose responses to know what range to work in.
So how different are the actual doses that give the effects that we're seeing? I mean, my question, I guess, is, are the nanos more efficient? Are they more potent?
Well, they're all at non-toxic doses. So we went up to, I've got those in there too if you want them, but everything was equal survival. Because I know that sometimes, this is a problem with, I'll say it now, this is a problem with nano papers, because you get a chemist who said, you've got to have micromolars being the same. Then you'll get a biologist who said, no, you've got to have equal survival. And if you've got because I've seen it with a friend of mine, if you have an editor who doesn't understand the difference between biology and chemistry, which many of them don't, some of these papers are in great trouble. Mm. And I saw a beautiful paper the other day, which I said should be accepted as it is. Came back, it was rejected because the person who was reviewing it said the doses are too high. If you don't work in different disciplines like genetic toxicology, you have to go up to the highest dose you can manage without toxicity. If you're a pharmacologist, you don't do it that way. So how can you ever get these sort of papers published? It's a big problem in the nano field. Anyway, I've said my piece now, but so.
Now I think the structure in nanoparticles is extremely important, so you may have diverse structures.
Right. There's another paper that I just recently reviewed, which says you've got to think of the structure. That was for PNAS. Again, I thought that was a very nice paper. Somebody comes back and said, you know, if you're going for structure, you're going for molarity, if you're going for all these different things, how do you ever get these past referees? Because the person who reviews it only concentrates on the bit that they know about. So it doesn't always, you know, you've got to get it to a system where you can, we know that it works like this. The system, the structure is not such an issue, but I know I've seen the papers which say if you get a triangular structure or whatever other structure, it alters the response.
Yeah, the structure might affect the whole physics and chemistry. So you may have the same compound with different structure, different effects entirely, which I think it's not quite perceived by chemists.
Well, as I say, I don't know how one of them is going to get together with all this, but all these different people with different ideas on, you're measuring biological issues here, that's what we're measuring. But if you've got a structure fanatic, or you've got a molar fanatic, or you've got somebody who doesn't understand survival, how the devil do you get these things refereed by the right people?
I was wondering if you have any insight into molecular mechanism of action, and related to this, have you tried making a nano version of the COX-2 specific inhibitors?
A nano version of the castrogen?
COX-2 specific, like Celebrex or Vioxx?
COX-2 specific inhibitors.
COX-2, no, we haven't, we just know that that's what they are.
Thanks. Okay, Dr. Davis, last question, please.
In the cancer patient who's being radiated or exposed to agents which increase...
Not the patients, sorry, it's the blood. It's just the blood that we take out.
No,
it's all in vitro. You understand, sorry.
Yes, I understand that. What I'm asking is whether ibuprofen and aspirin in the cancer patient should be discontinued if, in fact, they are helping repair double-strand DNA breaks. In other words, you're talking about patients without cancer and a protective effect, which is very interesting. But in the patient who already has cancer and then goes to radiation, are you in fact helping the tumor repair DNA breaks?
Well, what I can say about that is we're in the process now of looking. Let me just say one other thing. I just know where to start on this one. But in our test, which has been just given this money by the government, we don't know what the mechanism of action is. We've done it the other way. Most people look at the genes and things like that. We started the other end, look at the genome. So we don't care what the mechanism is. All we know is that you bash a cell on the head with one of these chemicals, and what you get is genome damage, which is DNA damage in the comet. We are now looking at some patients. I suspect it is a repair. It's one of the things that's involved. It could be many things, inflammation. But most of our cancer patients, the damage stays up. It just straight up. It doesn't come down at all. Whereas in the COPD and the others, it comes back to control levels. Okay.
Okay, well, we are out of time. Thank you very much. I'd like to present you with the keynote speaker certificate.
Thank you very much.
Thank you.